Welcome, everybody. So we're going to continue this talk and talk about fault injection, the same as the last talk, but the target is going to be different. So in this case, we're going to talk about hardware wallets and what we can do with fault injection on these devices. So first, let's start with what is a hardware wallet. And some time ago, when cryptocurrencies became popular, a number of manufacturers realized that there is a need for a secure device. And the idea is your PC is most likely compromised, and you need some kind of secure device which can be very limited in the APIs, have very limited attack surface, and then you keep your keys there. And you generate the keys on the device, and the keys never leave the device. So you plug it into your PC or connect to your smartphone, and you sign transactions, but the keys always stay on the device. And that's the whole idea to make these devices secure. And here on the slide, you can see three most popular hardware wallets. So it is Ledger, KeepKey, and Trezor. Not all of the hardware wallets have the same architecture. Ledger quite different, but KeepKey and Trezor in this case, they are quite similar because initially there was Trezor and it is open source, so anyone can make their own clone. And KeepKey has the same chip and very similar firmware as the Trezor. But today we're going to focus on the KeepKey. So that's how it looks, and all it has is the screen, one physical button for the user to approve operations, and a USB connection to the PC. And all the communication is done over the USB. So the screen is not touch, so you just can only press the button. So why KeepKey? Well, when you make a secure device, you have to make a number of claims how secure it is. And for example, here you can see from the website of the manufacturer, it says that if you lose your device, the pin protection renders the device useless even if it falls in the wrong hands. So what happens when it falls in the wrong hands? That's what happens. So someone builds a setup and they try to use physical attacks, for example. Another thing you can see, for example, on the Amazon description, that it says that it's bank-grade security that is simple. And that's something we want to put to the test and see how secure actually it is. Also something to mention, I didn't research the previous publications on this when I started the tests, but at some moment I found the presentation at DEF CON on Trezor. So it was 2 years ago or a year and a half. They presented the attack on Trezor, and as I mentioned, they have very similar hardware, so the physical attacks on Trezor might also work on KeepKey. So what they tried to do is to use voltage fault injection on the device, and their conclusion was that it is inconclusive because they didn't manage to glitch using voltage the unmodified Trezor device. So what they did is they built their own clone, and they had more control over it, and then they managed to get some results, but not on the real-life device. And of course, there was this comment on one of the slides, and of course, challenge accepted. Something about features of the KeepKey. It has STM32, and this is another reason to try physical attacks, because this is just MCU, it's not a secure chip. It has internal flash, and so you cannot do some simple attacks, just read out the keys with a physical access. It has quite a few commands you can send over USB, so there are 22 commands you can send. Pin protection, it is fully open source, so you can have the bootloader, the firmware, the source code, and so on. And it has verification of the firmware, it has flash protection, and it verifies the images running on the device using 3 it has 5 keys, and it uses 3 of them to verify an image. So every image is signed with 3 keys. And actually, for our attack, for physical attack, it is quite painful because we need to reset the device quite often, and it does 3 elliptic curve signature verification, which takes a while, and the device boots 2.5 seconds, so it slows down a lot. Maybe even could be considered a countermeasure. How does it work? So initially, when you have a device, you have something like that, you plug it in, and you need to initialize it, and it generates the keys on the device, and you get these 12 words which correspond to the master key on the device. And this is used for the backup. So you have your 12 words you write on the paper and keep somewhere safe. And if you lose your device, you restore using these 12 words. And when you use the wallet, you plug it in. If you need to do something security sensitive, you need to enter the PIN, and they show you this matrix on the screen. Since there are no buttons on the device, you need to type your PIN on the PC. But as we said, the PC could be compromised, so there has to be some kind of solution. And what they do for that, they print this matrix on the device, hence the title of this presentation. And it is scrambled every time with a random combination, and then you need just to press corresponding buttons on your laptop or PC to enter the PIN. So every time you enter random digits. And something about hardware. So it has STM32 and it has 1 megabyte of internal flash, and there are a number of different partitions of the flash. So there is some secure storage here for storing the PIN and the user data. There is bootloader, and there is a firmware itself, which has the applications for the cryptocurrencies. And it supports a lot of them, but it is just one monolithic firmware. And finally, why are we going to do hardware attack? And as I said, it is quite popular open source project, so a lot of people looked at the code. A lot of issues were fixed. The current version is 5.10.2 or something like that. So there were a lot of new releases, and a lot of issues were fixed. But on the other hand, they use general purpose MCU, and there is a chance to use fault attacks, because these general purpose MCUs are not designed to withstand such attacks. And well, initially, I got this device to do, because I thought I have a vulnerability in the code I found, and I wanted to make proof of concept, but when I got the device, it was already fixed because there was a new version. And then I had no possibility to exploit it using software, but then you can still try to do some hardware attacks. And that's what we're going to do now. So something about fault injection, just a few words. I will not talk a lot. There are some papers and a lot of research in this area, but the idea is that there are some specified conditions in which you're supposed to use your chip and some in which you're not. For example, chip expects to have a stable clock and to have stable voltage. So this device powered by USB power. Or it expects that there's no EM process around it, and no one shoots lasers at it, and no one freezes it, or no one heats it up too much. So all these restrictions are there, but if you mess with this, you can try to affect the chip in a specific way. And well, the common results of fault injection that you can corrupt data at some moment of execution. So you can corrupt it to zeros, you can corrupt it to FFs, you can corrupt it to some random value, or just do a few simple bit flips, so you just flip one bit at some place in the byte, and so on. You can also corrupt instructions when they execute, so instead of one instruction, another one is going to be executed, or you can, as a edge case, you can skip instruction if you corrupt something to NOP or something like that. So these are most common outcomes of fault injection, and we'll try to use that to actually exploit the device. Well, first, what you have to do is, of course, open the device. Here on the table, it has no case, it's just one PCB. First, of course, not always you have to open it. I tried it without opening the device, but it has aluminum case on the back side, so it's not possible to glitch through. And on the front side, it has PCB and the screen in front of the chip, so it's not always also very easy. That's why you have to crack the case. And well, that is a setup on my desk some time ago. As you can see, it's very precise and scientific, and you have to be careful with this. You can see I use XYZ table there on the back of the picture. There is no XYZ here because I couldn't fit it in on the airplane with me. So I had to leave it there and just bring the rest and just try to put it by hand carefully, close enough to do the glitching. Well, we have the setup. We need to try to test and see if we can affect the chip in some way. And for that, we can normally do in the lab characterization of the chip. Ideally, you would like to run your own code and execute it and put nice triggers, like raise the pin up just before the operation, do something simple like copy in and raise the pin down, then you know when it exactly happens, and then you glitch there. In this case, as I said, the flash is protected, so it's like real-life case. I had one device on which I tried that, and I couldn't execute arbitrary code, so I had to use what I had there in the firmware. And that is the simplest command I could find there, available over USB, and it's just a ping command. So you send some data up to 256 bytes, and you get this data back, just to test that the communication works. And what it does there, it does the mem copy of the message back to you, and that is it. Well, that's what we want to do. We want to glitch here. We want to glitch the mem copy and try to see if we can corrupt some data, and it should be easily visible because we get the data back from the device, and we can see if we affected mem copy the way we expected. And as I said, no code execution, so it is really painful to find a place where to glitch. You can see this is the data line of the USB communication, and that's the command we send here, and the response we get, and there is 1 millisecond in between, and the chip runs at 120 megahertz, so there is quite a lot of stuff could be happening. And you could try to be smart and find the way using the power consumption of the chip, but you can also try to brute force just to glitch everywhere in this region and see when you're affected. Of course, it will take longer, but it also requires less thinking. So I just brute forced. And that's what you get. So I said you have XYZ table. It is quite precise. You can move the probe just few micrometers at a time, and you scan the full chip again and again with different power and different timings, and you get such kind of picture. I don't have the layout of the chip, what's underneath, so I only know on the outside. You can see there is a block which really affected a lot by the glitching. And just to explain, so the green ones, the green dots, is when we tried to glitch, but we got no corruption. So we send the hello world message in the ping command, we get it back, and that is green. Yellow ones is what we do the same, we send the message and we get no response back. So we just glitched too far and we corrupted too much and it doesn't respond anymore. Then we reset and it works again, but we got no response from the command we sent. And of course, the most important are the red dots, and these are the dots when we send something in the message and we get the response back, but it's not what we send, it's something different. And that's what we mark red because we are actually interested in these dots. And well, that's the moment to do the demo. I started it in the beginning of the previous talk, just to have a bit more time to do the glitching. You can see here, this is the setup running here on stage. And well, to the best of my knowledge, it's the first demo live of EMFI fault injection on a real target. And we got a few glitches here. You can see we got 4 glitches. Success rate is quite low. Yesterday in my room in the hotel, I managed to get 2% success rate with the same test, but it really depends on the place where you put it. And I cannot be precise because the table really shakes a lot if I move around. you can see if I move away from the tip, it doesn't glitch anymore because it really has to be very close to the probe, to the coil. So that's the glitching. What kind of results do we get? We can see here maybe, I don't know if it's really visible, so this is the current running test, and that's quite sad actually what we got. We just corrupted to one letter. Instead of sending 10 back, we glitch the mem copy and get only one back, only one message, only one letter. But of course, you can imagine that if we just corrupt them, okay, somehow it doesn't work anymore. Yeah. If we corrupt just one character, we can get better results. So that's the demo I've done before. I will not show it because we had some glitches here. But these are the results I got before. And you can see that in this case, we corrupt the length of the mem copy quite a lot. And we can set it to some value. And quite often it's less. So we send 10 characters and we get less. And one time or two times we got 11 characters. And you can also imagine if we corrupt it to something big like 200, 400, or megabyte, we can get more memory. Well, if we corrupt a megabyte, we're not going to get anything. But if we corrupt to something reasonable, we can get more data from the device and get basically buffer overflow using fault injection. So this is more results I got before when I just first ran this characterization on the device. You can see that in the different parts of the chip, I was still scanning the full chip and try to glitch, and I got a lot of different results here. You can see often we corrupt the length and we get just less characters back. Sometimes we corrupt 4 characters and they set to 0. Or we can corrupt it like these bold ones. They have 1 bit flip in the character, so the capital D and lowercase d, they in ASCII just 1 bit flip from each other, 32 in decimal. So we corrupt 1 bit and we get this kind of results. And you can see the last one on the bottom. It's quite interesting because we got something we didn't expect at all. It says settings applied. We send hello world and we send ping command and we get back settings applied. And that's quite unexpected. It's hard to tell because it's a black box. We don't see what's happening. We just glitch there and corrupt something. One explanation could be is that when we copied, we corrupted the source to the string which says settings applied, which is present in the firmware, which is not very likely because it's difficult to corrupt it exactly to the beginning of the string. And it could be, but another explanation could be is that we corrupted the PC register and just jumped to another instruction. And this is one of the commands. You can send a command which applies settings. So if we corrupted the PC to the place where this instruction is executing, and in the end what it does, it prints settings applied and it returns the message back to the user via USB. So that could also happen here. Other interesting results, so this is the screen. On the table here you can see I have no screen. I had one device and I was glitching it for in total maybe 4 or 5 million attempts over this past half a year. And well, I killed the screen and one of the LEDs, they do not work anymore. But the chip still works, it boots and it runs the firmware and USB works, so for the rest it's still fine. And it has still keys and pins, so you can still use it. But you can see what you could see on the screen when you glitch. Sometimes you get error detected and reboot device message. That happens at some moment. They check CRC on some data copied, and we glitch somewhere there, and it prints this message because it detected that CRC doesn't match anymore. Other one says that clock instability detected, and you need to reboot device. And we'll talk about this, what it means a bit later. Just a few more screens of the glitching. So you can see we corrupt the start of the screen and we print just from the random place. And we get these messages. They don't really matter, like you're not going to exploit it like that, but it's just nice, nice pictures. So why clock instability detected? This is the source code, what it says in the firmware. So the manufacturers of the hardware wallet, they actually cared about fault injection. And they added this check, and what it does, it checks some registers, and it is used to prevent clock glitching. As we talked in the beginning, you can use not only voltage or EM, like in this case, you can use clock, and if you give faulty clock, which skips cycles or changes frequency, you can try to affect the execution. And that's what they try to prevent here, and as far as I know, this is the only fault injection countermeasure present in the device at that moment. And we see we trigger it sometimes, but that's not our idea. We don't want to trigger this countermeasure. We try to avoid it and corrupt something different without triggering the check. So that is nice. We can corrupt mem copy, we can corrupt the screen output, we can get some nice pictures, but is there actually exploitable glitch, something we can use in an attack on the device? Well, that's something we're going to try next. This is the first command I tried. It says change pin, and of course that's something we want to do. Pin is one of the countermeasures, security features on the device, and another one is passphrase, but passphrase is not recommended for average user, only for advanced ones, because if you forget your passphrase, it's going to be lost forever. You cannot restore your device. That's why on the side of the manufacturer, they say you better not use it unless you're really sure you want to use it. So on most of the users' hardware wallets, I can imagine that they just have pin and nothing else. So if we can change the pin to something we choose, then there's no protection left on the device. That sounds nice, and that's what we try. The change pin command, it says if pin protect, and at this moment it asks you to provide the pin. If you didn't, it asks you to provide the pin every time, and you have to enter the pin on the PC and send it, and it shows you the scrambled matrix and so on. And then if it is correct, then you can modify to another pin you choose. So we want to glitch this if statement and hopefully skip it entirely. So do not do this check at all and continue. And right after that, we can enter new pin, and we're done. Well, it wasn't that easy. It was a fail. I started glitching and glitching and glitching, and I spent maybe a few weeks or a week of glitching, and I got no results at all. Like, I never skipped this if statement. And then I looked a bit closer, what's happening. So I sent the command, and as I said, we have no trigger when this execution starts. So all I do is I trigger on the USB packet I sent, and then I just wait for some time and glitch. So I try to reduce jitter as much as possible. But you can see here, you have to press the button. And it's like a security feature to ensure that user actually wants to change the pin. You have to press the physical button and say, yes, I do want to change the pin. So of course, in the beginning, I implemented some relay board which does the clicking, and you need to hold the pin for the button for 1 second exactly. And I had some FPGA which does exactly that. So it, with no jitter, almost no jitter, it presses the button, and it releases it. So I know exactly when I release the button. But the execution itself, what the firmware does in this loop, it's not deterministic. It has quite a bit of jitter in this execution. So after I release the button, it doesn't execute right away this, or after some fixed delay, this next part. And I have a lot of jitter in this part. And having these random delays before the if statement, this is actually a countermeasure common for devices which try to protect against fault injection. So you add random delays here, and it's very difficult to hit this if statement. So this attack could be still possible, but maybe it would take me half a year to run non-stop in the lab, and then I would hit it one time. Or I need to come up with better ways to find the exact place on the trace when this if statement happens. So of course, it was too much work to continue here, and I just moved on to another command I can send. And this is the reset device command. We send some parameters on to the device, and it is supposed to be used first time when you just plug in your device first, and you initialize it with a label and language and the pin protection. If you want to use pin, you can even disable pin on this device. It's one of the possibilities for the user not to use pin at all. if you use pin protection and set it to true, then you can set a new pin and so on. And you can see here in the beginning, it checks if the storage is initialized. So if the user already put the pin, if he has his own keys and he used this wallet before, when you send it, you get the wipe device first message. And we want to do the same as before. We want to skip this if. We do not do this check. We go right away to reset init, and we update the pin here. So all it does, it updates the pin. It doesn't wipe the device. It does not affect the keys. All the rest stays in place. All you change is like label, language, and pin. And you can choose even if you want to change them or not. So you can just choose pin protection and change the pin. So that's what we do. We glitch here in the if statement, and it was successful quite fast. And what we managed to do is we send the command reset device, we glitch there, it skips the if statement, and it asks us a new pin, and then I changed the pin, and then I resetted the device, and then I couldn't enter the pin. When I entered the pin, it was wrong. So actually, the attack didn't work. But then I had to figure it out, and it seems that in the reset device, what it does, it changes the pin in RAM. So when you boot the device, it does shadow copy of the flash storage to RAM. And when you do reset device, it changes pin in RAM. So that's good so far, but would be nice to have persistent one glitch and then persistent change. And that's what you can do. So you do, if you do it in a sequence, you just need still one glitch. You send the reset device command, you glitch here one time, and you change pin on RAM, and then you send the change pin command, the one we used before. But this time we don't need to glitch anymore because we have our pin already in RAM, which we just corrupted when we done the glitch on the reset device. So we have our own pin in RAM, we send change pin, and change pin is going to check it against the pin in RAM, and we can set another pin or whatever we want now, and it's going to be written to flash. And it also writes only pin, the keys are not affected by this. And combining these two calls in just one single glitch, we could bypass the pin check. So that's the full attack, how it works. Also on the next slide, how it looks. So you get the device somehow, you do this, you glitch it there. User already should have initialized the device and have the pin set and the tokens on the device. The keys for the cryptocurrencies. And then you do change pin command, you glitch, you change it to something else, and it's written to flash. And from there, you have the user device, and nothing else changed but the pin, which you know now. And you have the full access to all of the features which the user had. Of course, as I said, for advanced users who actually use the passphrase, you're not going to get everything right away. So you need to combine the glitch with something else, and then to get the stored secrets on the device, and then brute force it offline. So it's a bit more hassle, but as I said, since the manufacturer does not recommend average users to use this, most likely most of the devices will not have this enabled, and then you can just do this simple glitch attack. Something about results. That was in the lab, so when I had a nice setup and I could find the sweet spot where I can glitch easily, I got success rate of 1.2%. And this is success rate not for the whole attack, but for every attempt. Every time I try to glitch, every time I reboot the device and send the command and send the glitch, on average I would get like 1.2%. So an attempt rate is 0.3. So I need to wait 5 minutes, send a few hundred glitches, and then I skip the pin. And that is it. Well, something about conclusions. Well, that's what you can do. If you have MCU on your device, and you call it a security device, and you have no countermeasures in software, or they are very limited to some specific type of fault injection, for example, clock glitching, that it's not going to prevent an attacker from using other kinds of physical attacks to try to bypass your security features. And finally, if there are no vulnerabilities in the source code of your device, in the firmware, it doesn't mean that this device is secure. There could be still some attacks on the device. Well, that is it. The last picture I wanted to show is that I got it one moment at glitching. I was corrupting the screen output a lot at this particular delay. And what I think happened is that instead of printing this string I expect, so it should have said something like, do you want to really change the pin? It corrupted the string pointer to something else placed in memory. And you can see a few ASCII characters and all the rest is unprintable on the screen. If you have any questions, I would be happy to answer.
Thank you for your presentation. I may have missed it, but I don't think you mentioned which hardware do you use to inject fault, how much it costs, and what are the practical problems with setting up the lab and stuff like that.
Yeah, so that is something I really didn't mention. I use the proprietary tools from Rescue. I'm from Rescue, and of course I have the lab next to me, so it's quite easy to get all the tools. It is not very cheap to use this equipment. I don't know exact prices, but you cannot just buy this and for a hobby project and use it at home unless you want to invest quite a bit. But as you've seen, for example, in the lab, we always use XYZ table. For this glitch, I don't use XYZ anymore. You lose a bit in the quality, but you still can do some glitching. So you can remove quite a few parts from here. It will take more time to set it up, but with the investment in time, you can replace quite a few parts. There's also open other solutions like cheaper ones, for example, chip shower or something like that. Or you can use lighter, as you've seen from the last presentation. You can create EM field using simple lighter. Maybe it also works. But yeah, you can reduce the cost quite a lot, and that's the question: can the attacker do that or not?
Hello. Thank you for the presentation. I might have missed the point if the information is already in the flash and you're already doing hardware voodoo. Why exactly are you not just changing the flash value or reading out of the flash what you're interested in?
Yeah, exactly. So if you can read flash, that is it. You can just read the contents. It's plain text. But as I said, they have the bootloader, and bootloader verifies signatures, so you cannot write anything there on the device, like any code you want. So you cannot read it from the software. From the hardware, the flash is internal on the chip. So I have this STM32 It has 1 megabyte of internal flash. You cannot just connect something and read it directly. And also they have flash readout protection disabled, so it's set to the, so you cannot just read the flash with external tools connecting to the device.
You didn't mention also how you chose the point where you inject the fault. You did present the heat map of where the fault were, but what made you choose a particular point, or which point did you choose?
Well, when I was doing the test, I was just scanning the chip and see where I get better results, and then I stopped there. But now when I do the glitching, so I do it somewhere here in this area, but of course by hand you cannot be that precise, and it's like maybe half the chip, and the probe is quite big, so it's like 1/4 of the chip, and I most likely affect these parts here and do the corruption. But you just have to scan and to find the place when it's like the best for you if you use XYZ, or keep fiddling by hand and trying to find it if you use a setup like this. And also, I try to find a place for the glitching now on the stage to have like half yellow, half greens, and then you have a higher chance of affecting you. If you are in the spot where you get all the greens, it's very unlikely because you just don't affect the chip at all.
Hi. I maybe have two questions. So first one, why did you choose EMFI over like VCC glitching, for example? And second one, what frequencies are that you can send multiple glitches with EMFI? Or do you have to wait in between?
Why I chose EMFI? Because voltage didn't work for me. I didn't want to try too much, but I tried to desolder the capacitors. It's powered over USB, so it has a bunch of capacitors there. I tried to remove all of them, and then it stops working. If I keep few of them, it doesn't glitch. I could desolder the chip and do more soldering work, but it's like not something very interesting for me. So I moved on to EMFI because you have to change the PCB less and just to try affect the chip. And also you can get better results because you just affect some parts of the chip, not the whole chip. And it also has USB on the chip within the SoC. So if you use voltage, you will affect the whole chip and affect USB and affect the CPU. And then very likely you will just crash the USB and you will not get any response. Even if you had a successful glitch on the CPU, you will not see the response and you will not know if you did something. For the second question, what was the second question?
So how long do you have to wait or to do multiple glitches with EMFI?
So you can shoot a few glitches at the same time, right after another, like few microseconds in between, if you really want to. But for me, I really want to affect one spot. There's like one check or one instruction, so I just do one glitch at a time. And when I want to do next attempt, I need to wait. If I get the green ones, normally I don't reset, so I can try right away. So it's like maybe 1 second in between. And if I got yellow, so the device was mute, I had to reset the device, and then it takes 3-4 seconds to reset, and then continue again. Thank you.